Next topic, let's talk about how to use average rate of change to identify linear functions. So earlier we have a function f of x equals negative 3x plus 7, and then we graph that function, remember? And then find the domain and the range. So now if we choose some x values and then plug into the function evaluate y, okay? And then we choose all those x values and then evaluate y, corresponding y. And then we see the rise over run, right? Rise over run. Rise, that's the difference between two y coordinates divided by difference between two x coordinates. And then we will see they have the same ratio of change, right? We call that average rate of change, okay? It's a ratio of two changes, the difference between two y coordinates and the difference between two x coordinates. That's why we call it average rate of change. So if data is a linear functions data, and then the average rate of change, which is the slope of the line, should be the same constant. Okay, they should be the same constant. So that is the criteria how we identify whether the data set is linear or not linear. All right, so we already learned the slope before. Now we introduce another concept. It's called the average rate of change of a linear function, okay, which is the slope of the line. Okay, but if there's other function, it's not a linear function, and we can also calculate average rate of change. Okay. So now let's look at an example. There are two examples here. We're going to do one by one. A is a string of E. coli known as this is placed into Petri dish at 30 degrees Celsius and allowed to grow. The data showing in the table 2, which is on next slide. The data are collected. The population is measured in grams and the time in hours. Okay, this just explains what the data is about. And plot the ordered pair in a rectangular coordinate system, and then use the average rate of change to determine whether the function is linear. All right, so now let's look at the table. Okay, so first column, that's the time in hours, and the second column, that's the population. Okay, unit is gram. So that's form an ordered pair. And then in order to determine whether this data is linear or not, we need to calculate a rise, okay, which is from 0.09 to 0.112 is increased by 0.03, right? And then from 0.12 to 0.16 is increased by 0.04. And then we can do the rest of it. And then the run every time increase by 1, right? Therefore, rise over run, okay, or difference between two y coordinates divided by difference of two x coordinates, we got different number, right? For this two, that's 0.03 and then 0.04, 0.06, 0.07, 0.10. So there are different numbers. Therefore, this data is nonlinear. If linear data, those numbers are supposed to be the same. Okay, same constant. All right, now let's look at the B. The data in table 3 represent the maximum number of heartbeat that a healthy individual of different ages should have during a 15-second interval of time while exercising. Plot the order pairs x, y, and use the average rate of change to determine whether the function is linear. All right, now let's look at the next data. So x every time increase by 10, right? That's the age. And then y every times what? From 50 to 47.5 is down 2.5, right? From 47.5 to 45, also down 2.5. And then you can calculate all of them. The difference between the 2y is negative 2.5. And then the difference between 2x is 10. So we can calculate negative 2.5 divided by 10, that's equals negative 0.25, right? For all of them, this is the same number, negative 0.25. That's why we say this data, it is linear because they have the same average rate of change. All right, the book gives the detailed explanation. You can read through it. And then if we graph it, okay, for the A, population versus the time in the unit of hours, if we plot those data, and then you can kind of tell this is a curve, right? Not a straight line. If it's straight line, if it's a linear function, it's supposed to be like that, right? So from the graph, we can tell too, the data is nonlinear. If it's a linear function, the graph is supposed to be a straight line, not a curve, right? So for the B, this is a calculation for table 1. Okay, you can see we calculated earlier the average rate of change. They're all different numbers. And then for the part B, if you plot the order pairs, okay, that's the point in a rectangular coordinate system. And then if you connect all the points, that's a perfectly straight line, right? So that means the data, it is linear, right? And then that's the calculation, okay? Calculate average rate of change. They're all the same constant. And then we can say, we can conclude this data is linear data. All right, so there are two ways to determine whether the data set is linear or nonlinear. First is calculate average rate of change. 2 is from graph. Okay, if average rate of change is the same constant and then data is linear, otherwise it's nonlinear. From graph point of view, if you plot all the points and then connect all those points, form a straight line, and then data is linear, otherwise it's nonlinear.